Hello, everybody. Welcome to WAVY Science Lab. I'm meteorologist Jeremy Wheeler, and we are going to be talking today about temperature, and we're going to have all kinds of details about temperature, the history of temperature, about some of the instruments, and then how it pertains to weather. So it's going to be kind of a broad topic today, but at the same time, it's one that's it can be fun. It can be a little nerdy. It can be a little fun. So we're going to have some fun with it, but we're going to get a little into the weeds with, as my Tai Chi instructor often says, into the weeds about the history of it a little bit. And maybe there'll be some different levels here. So let's get a start on it, and we're going to get right to it and talk about the temperature. What is it? So basically, the temperature, how hot or cold something is, basically, what does that mean? I mean, it's as basic as it gets. I mean, right now, it's hot, it's cold, that's the temperature, right? If it's, you touch something like a hot pan, then, there you go, that's hot. So let's get a little more in depth with it, and that definition's good, but we can do better. So the scientific definition: average kinetic energy of the particles in a system. Wow, that's quite a bit, isn't it? So we want to break that down, and basically, let's break down it word for word. So average, the number that represents the data. For instance, if you have one day, somebody brings a donut into the office and gives it to you, hey, great. Number two, day two donuts. Day three, there's three donuts. So you average that up, you add them up, divide by the number of days, you get an average of two donuts. And so, that number represents the number of donuts you would expect then going forward on average. So the average kinetic energy in a system. So it's different from heat, right? Because temperature kind of takes a snapshot of what's going on, but heat is kind of the total energy in the whole system. So let's take a look at it, and let's put this in full, and we're going to do an experiment. The experiment. So let's talk about this. This is Frankie the snowman. It is Frosty's long lost cousin, and he's in an oven. I hate to say it, but he's in an oven. Okay, all right. Yes, there's no way to put it. So we're going to add some heat. We're going to increase the temperature, and those little particles in there, the air particles, they start heating up, right? And so we add some flame, some fire, and so now those particles are bouncing around a little bit more. They get more energy, and they move faster, right? So the energy increases, and then, if we increase this even more, then, oh no, Mr. Bill. He melted. All right. So we turned up the heat. The particles are bouncing around, a lot of energy in there in the system. And so the temperature is, it's way up. And unfortunately, Frankie melted. But fortunately for him, I got the time stone on loan from Dr. Strange, so we can reverse it. We can go backwards. And so let's go. There we go. All right. You're welcome, Frankie. Yeah, we're going to take it back even more, take it back to the cold. So now we got that temperatures back down to, lower levels. All right. So that's great. But let's talk about how we measure the temperature. The thermometer. Dun, dun, dun. Surprise, right? No, that's not a surprise. Everybody knows that. The thermometer, right? So that's pretty standard. Measure temperature by expanding liquid, or in some cases, the electronics in it. And we'll talk a little about that. We commonly use the degrees Fahrenheit and Celsius. So that's pretty basic, right? So let's talk about go back in time, talk about the history of it. And so the thermoscope is a simple tube and bulb with water. And, that's all it was. Galileo is often credited, but he didn't have a scale. So a friend of his, I believe, looking at the notes and looking like it was a friend or at least a colleague, Santorio, Italian, I believe, added a scale. And so, buongiorno. And so he added a scale, and then they went from there, and things just developed over time. Now they had a bunch of scales that developed after that point, a whole bunch of them, but they had to kind of agree on a scale, and so they did. Oh, let me show you one thing really quickly. I want to back up here, and I have a Galileo thermometer here, and it's on loan from Chief Meteorologist Jeff Edmondson. And so what it does is it shows you kind of these little liquid capsules. As this tube of water heats up, the density changes, and so these will rise and fall. And the original Galileo thermometer wasn't, this fancy, nor this, there's no scale, but here there is a scale. So that kind of gives you an idea of the Galileo thermometer and what it looks like. All right, so let's go back to the topic, and basically. They did develop a scale, and they agreed on a couple of them. So one was Daniel Gabriel Fahrenheit. Scale was 32 degrees for when ice melts, and 96 degrees when the average human temperature, and boiling point was 212 degrees. Also developed a mercury thermometer. Okay, so that was Fahrenheit. And then the competitor was Anders Celsius. And so he developed another scale. He said, hey, we're going to make 0 degrees when water freezes, 100 degrees when water boils. And it's now used by most countries. That's a metric system. So that is another one. So the Celsius metric units are easier numbers to remember. I mean, 0, 100, there you go. Fahrenheit, it's a finer scale. You have a little bit more. You can the scale of those ticks on the thermometer there. And so you can kind of see the difference. And so, different countries use these differently. Now, there's another scale. This one gets a little bit nerdy. And so this one is the Kelvin scale. Absolute zero is, no particle motion. So that's, deep space, nothing. Well, actually, deep space, I think that's 7 degrees or something like that, Kelvin. But bottom line is there's no particle motion when you have absolute zero. So that equals minus 460 degrees Fahrenheit. I mean, wow, that's really something. That's some cold stuff right there. I mean, I wouldn't want to touch that. So your hand would probably freeze automatically. So let's talk about one more thing here, and that's eventually the mercury was phased out, right, in these thermometers, because kids would, end up playing with them, and that's no good. And thermocouples were invented in 1800s. I was a little surprised about that, where two different metals join, you can create a small voltage. And so I've got one of those right here, and basically that is a digital thermometer. And so inside of there, they can measure the temperature exactly. And then I've got another one. This is an alcohol thermometer, most likely. And so the alcohol inside, heats up and expands or contracts. And this is calibrated, it's measured. And so that's another one. And then there's another one here. This is one that on the back, it's got a metal, a foil metal, and that heats up and expands according to the temperature as well. All right, so we're going to take a break now. We saw a few things there, but we're going to take a break. And when we come back, we're going to talk more about some of those instruments and a little bit about weather and how it pertains to weather. All right, we're back. And let's talk. Hello, everybody. I'll just Jeremy Wheeler magically appearing, and so, apologize. And we also have the invisible scientist with us as well. Yes, welcome. Hello, everybody. Okay, so we're all about temperature, and so we want to talk now about daily use for living. Right? We use temperatures, all the time, mostly just to know how comfortable we're going to be inside, outside. We want to get outside. What's the temperature going to be? And so we have. A whole bunch of ways to do it. I showed you the instruments, but this is, what it looks like. And this is the temperatures, and pulling it up right now. So there we go. So these are the temperatures outside today, on a certain time. And so at each airport around the area, there are thermometers and military installations as well. And so we get those reports in, and then we give them out to the public. So this is on our graphics system, and it shows what's going on. Now, there's temperatures at the surface. There's temperatures aloft. So this is kind of a layers of the atmosphere. The first layer is the troposphere. And so that goes up to about 33,000 feet. And you can see the commercial jets fly, up about that height, a little above, a little below that, of course. Clouds are in that layer. Some clouds extend up to the stratosphere, the very bottom of it, but that's maybe the tropopause, but maybe a little bit into the stratosphere. They kind of overshoot, those overshooting tops from the thunderstorms. All right, so this is the layers of the atmosphere, and you can see the 4 layers. So we're not going to go into that too much, but I want to show you kind of the temperature layers. So in the bottom there, you have the troposphere, the temperature's dropping, right? And so as you go up in height, the temperature drops. We're pretty familiar with that, right? You go up in a mountain, it's colder. You go up in a plane, it's super cold up there. You just, you go up a weather balloon. But at some point up around 33,000 feet, a little higher than that, you got what's called the tropopause. So the ozone layer's in there, and you get some heat, and so that starts heating up the stratosphere, the second layer. That's why the red line starts going up. And so it increases and increases and increases, and then it goes up to a certain height, and then it starts cooling again, the mesosphere. And then up in the thermosphere, you get a lot of that radiation from the sun, and it heats up those particles, but there's not a lot of particles up there. So it would still be cold to you and me, but I mean, the temperature technically is high because the particles are just going around like crazy, but there's just not a lot of particles. So that's kind of the difference there. And that's the difference between temperature and heat that I talked about. So the temperature's high, but the heat is not that much up there in the upper levels. All right, so the temperatures, that's at the aloft, but let's talk about what's happening at the surface. And so you get these hot spots, these pockets of warm and cold, and then you get boundaries between them. This is a warm front, and so a warm front means that your temperature is going to go up. If you have a cold front, of course, it means that your temperature is going to go down. That it's just that simple. And so these are temperatures at a certain point, and you can see the hot air there in Texas. You can see the cooler air by us, and these hot and cold air masses just move around all the time in the form of fronts. And so, this is a surface map that shows kind of that very same thing. And you can see the cold front, the cold air is coming in behind it. There's some snow on this map to the north. There's rain around the low because that's what happens around low pressure areas. Warm front to the east of the low, and so you got the warm air coming up and bubbling up on the side of it there. So this is a kind of a typical weather map, and there's also, this is the air temperatures, right, at the surface, and then we can measure the temperatures aloft. I showed in the other podcast, rather, I showed that we have the weather balloon, and so that goes up and measures the temperatures aloft. And so we can measure, what's going on at the surface and aloft, and then the computer models take those numbers, the temperatures, and all that information, and they crunch out what's going to happen in the future. And so it'll spit out, the temperature forecast. We looked at the model just a moment ago, and I'll go back to it here. The surface temperature is, this is a model. This is a model forecast. It's not the current temperatures. And so it thinks, well, hey, today 96 degrees in Dallas, 82 in Norfolk, and there you go. And so they do a good job, but the thing is they don't always agree. And so my job is to try and figure out which model has the right idea as to what's going on. And that is not an easy thing to do. Let me tell you that right now. So is it really that hard? Come on, it's temperatures, right? Well, the thing is, you got to play a game of high and low. The models do a good job, but they're all created differently, so they handle the temperatures different. And that's the game. That's part of my job, trying to figure it out. But it is not always easy. I've had models some days split about 15 degrees apart, depending. That's pretty rare. Usually, though, they'll split every day almost. They'll split about 3 to 4 degrees apart. So that's meteorologists think, oh, you can always be wrong, right? Well, guess what? Our models are not exactly like rulers. It'd be like having 3 different rulers and all of them tell you different things and say, hey, which one's right? So think about that a little bit. Take it easy on us, all right? The meteorologist, it's a tough job. Okay, so that's the temperatures. I want to show you the surface temperatures, but also over the water, right? And so we measure that. And so sea surface temperatures, that's very important when it comes to hurricanes, because when you have a temperature over 80 degrees, then you can possibly get a hurricane to form. That's the fuel that they need, at least 80 degrees. And warm, deep ocean water is a big fuel source for them. And so, in this case, there's a lot of fuel. There's still, when I'm doing this right now, there's still, hurricane season, a lot of hurricane season to go. So that is the case. All right. So we talked about temperatures, and we talked about, how they're measured, things like that. These temperatures, they're, pretty simple numbers. And again, they're at airports around the world, so you can get temperatures around the world, and military installations and some other government places as well. And then we got the water temperatures. Now there's buoys out there that measure those water temperatures, but you can actually use satellites in space to measure the temperatures of the ocean as well. And that's a little complicated how that works. But the temperatures in space, actually, they do measure what's going on out there all the time. They're constantly measuring the temperature of the Earth, and so we get those. And then, we can display some of them, but some of it you use for climate, which is, the history of temperatures. And so a lot of climate experts will use that information, satellites and the temperature sensors. And then they'll also use things to go back in time, like tree rings and, soil samples, not soil samples, but lake bed samples, things like that. All right, so those are some of the ways that we can measure the temperatures. And so we're going to take a break here in a little bit. And when we come back, we're going to talk a little bit about how, this interacts with humans. And so, our lifestyle, our day to day. And we'll try and get a sense of, how we interact with those temperatures. So we'll have that coming up in just a little bit. All right, we're back, and we're talking about temperature today, and all about temperature. And we saw a bunch of things where, we saw the instruments, and we saw some of the software, how we display those temperatures. So now I want to talk a little bit about, how it interacts with you and me. And so, we've got the different thermometers here. A lot of times we'll look at this even in the weather center. And so it tells me the temperature, it tells me the humidity, which we're not going to talk about much today. That'll be another podcast. And so, usually in a home, a lot of people are comfortable in the upper 60s to low 70s. When you start getting, in the super summertime heat, it's hard to cool down your home. And so, that's a trick. But that thermometer is very important. So we've got the temperatures out there, the current temperatures, but then we've got also the forecast so that people know, exactly what to expect. So, sometimes it gets really hot. Look at those temperatures down around Texas. The temperatures looks like they get into the hundreds. The heat indices get even higher than that. The heat index is when you combine the heat and humidity together because, when you have really humid air, your sweat doesn't evaporate as effectively. So that's why we have a whole bunch of, try to remind people what's going on, stay hydrated, take breaks in the shade. So you got to try and get out of that heat. Lightweight, light colored clothing really helps because, when you have a really light shirt, a white shirt, it reflects the light. It doesn't absorb it and turn into heat. And then, of course, we remind folks to check on the elderly and the pets. And so something also happens is hot cars. And so unfortunately, some folks, they'll leave kids in cars. And so when they do that, you got to keep in mind those temperatures inside the vehicle can rise fast, especially when there's a lot of sunshine. The camera in the background not helping me out here, but when you've got a lot of sunshine, then you can heat up that car quickly. I mean, 10 minutes, 89 degrees, 30 minutes, 104, 1 hour, 113. So that's the greenhouse effect, right? And so I did an experiment, and I showed the temperature here. It was it was a sunny day. I did this a few days ago, and so it started off with the temperature about the same, right? I put the thermometers in the shade, and the hygrometers. Just ignore that. Just never mind. They didn't exactly agree, but the temperature about the same, and the clock on the right's tilted a little bit so that it may look different, but it's hitting about 80. So then after a short period of time, I put one in the sun, one in the shade. And so you can see, the one on the left, it was about 82. I think it was close to the sun a little bit there. But the one on the right was hitting close to 90 degrees. And that was after 5 minutes. And so, I mean, definitely a difference there. I mean, definitely. So, when you're working outside, you want to try and keep that in mind. You want to try. That's why you take those breaks in the shade, because the sun adds extra heat. Your temperature goes up even more. And so, when in the effect of the vehicle, the light comes in. It's like a greenhouse. You got your own portable greenhouse, right? So the sun comes into those windows, converts it over to heat, and then the heat can't escape. And so that's why your vehicle heats up so much on the inside. The car thermometer reads the outside, and they're modernized to where they do a pretty good job. If you're in a parking lot, you don't move, maybe it's not exactly a good reading, but if you're moving, they're designed to get a pretty good reading of that temperature. I wouldn't take it 100%, but still. And so, some folks have the thermometers outside their house. And so, their temperatures might be different from our temperatures. And you say, wow, my house reading, 97 degrees. How come you have 89? Well, think about this. There's a Stevenson box National Weather Service uses that box on the right. It's white. It's got gaps in there so that the heat can escape. And it's always technically the thermometer inside is always shaded, whereas the ones at the home might not be necessarily. And the white paint, it's important. It reduces the heat. They do have to clean them off once in a while. And these are usually at airports. They're placed about 4 feet above the ground. I thought it was 3 feet, but this says 4 feet. In an open field, trying to get it away from buildings, because the one on the left is right by a building, and that building heats up, and so you got to factor that in as well. And so we have the urban heat islands. That's something that it's a real thing. All that concrete, all that metal in the cities heats up, and the heat emitted from the cars and everything. That temperature in the city can rise up quite a bit. You get out in the fields and where the trees are, and your temperature can be drastically different. So your daytime high temperatures could be totally different there. And it makes a big difference to you in how you feel and where you go. You drive around that city, your temperature can vary for about 10 to 15 degrees even. So that's something that, when you talk about climate, that's something that they factor in, urban heat islands. They take the temperatures away from cities, of course, but sometimes, the cities sprawl and gets closer to some of those areas, those airports especially. And so, it gets really hot out there sometimes. So anyway, I want to talk a little bit. Well, basically, that is kind of wrapping up the temperatures and temperatures, how it feels for today. Just hopefully you learned a little something about that. I'm not going to leave just yet. We still got one more thing to talk about, but the temperature, it's very interesting, especially when you see these wild swings in temperature. Sometimes you get these cold fronts in here, and you get a huge swing in temperatures. So that's something that it's challenging. It can be challenging for me, very challenging. So we do our best. We do our best. So I do want to talk about the environmental tip of the day, and we'll finish off with that. So here it is. And so, inside, light equals heat, basically. Old incandescent bulbs added a lot of heat. Now, people switch over to these LEDs, so it makes a big difference. It also uses a lot less energy. So turn off the lights when not in use. That makes a big difference. You save money, and it uses less energy in your home, which is, if everybody did that, we would use a lot less energy overall, and it would really help out. Just some tips for you there. LED lights, light emitting diodes, pardon me. They used to use them on the old boards and, a lot of things electronic, but then they expanded them, and now they use them instead of the old incandescent bulbs, which was highly used back in the day, a long time ago. And so, it can save you a lot of money. And so now I don't even know if they sell incandescent bulbs anymore. I don't think they do, but there's other types of bulbs, so you can switch those over. Okay, so that is it for today. Hopefully you learned something, and hopefully you had a little bit of fun, especially with Frankie the Snowman, and the temperatures and the instruments. Kind of interesting to see. So I'm meteorologist Jeremy Wheeler. Thank you for joining us, and hope you had a good time, and everybody have a good day.